When I saw this recurse route, I already knew that you did not have an understanding of recursion.
Hmm.
And then you ended up spending the rest of the time just trying to go through the example and then patch your design. Do you actually go in depth to your design and try to bulletproof it, or do you just make one change to your design and then throw a new submission at Leetcode and hope that it works?
The latter,
Yeah.
unfortunately.
Yeah, that's basically what I picked up here when you kept trying to
Mhm.
patch your code and like, oh, this.
Mr. Chen, thank you so much for taking the time to conduct a mock interview with me. I really appreciate it.
Yeah, for sure. So I understand that you have an upcoming interview. It's
Yes, I have an upcoming interview next week.
okay. Tell me a little bit about yourself, your situation, and where you are in the interview process.
Um, so by myself, do you mean like my prior experience with computer science and so forth?
Anything that will really help me understand where to look for your I guess problems during the interview when you do these
Mhm.
mock interviews or anything like that.
Okay. Yeah. So I think the biggest weakness would be that, I am a junior right now studying computer science. But because, um, there like last year, I wasn't really sure if I wanted to do computer science or not. I am a little bit behind, um, on what my standing should be in my major as a junior.
Mm-hmm.
So, for example, I really only taken like two intro CS classes and intro data science class. I'm currently taking discrete math and data structures, whereas for most juniors in my college, at this point, they've already taken those,
Mm-hmm.
and they're usually taking algorithms, or systems programming.
Mm-hmm.
So I am a little bit worried about that. But in terms of my own self preparation, I've been reviewing, common patterns, the major data structures and algorithms by myself.
Mm-hmm.
And in the interview process, for most of the companies, I've only applied to them. And for a few of them, I've conducted, pre screening, like behavioral interviews. And for the interview next week, they gave an online coding assessment and an interview as well. So those constitute the first round.
I see. So, how have you done on those so far? Have you heard any results?
From the online coding assessments,
Mm-hmm.
I haven't taken any of them yet, but I'm going to take the online coding assessment for where I'm interviewing in a few days because, like both of them are in the first round. So I think they're going to use like both data points to see if I move on to like the on-site round or not.
I see. Yeah. So, I'll tell you that I've been in your situation before. Actually, when I first transferred over from community college to UCSD, I was in the exact same position, and it's quite. I would say it's not impossible to get to final round. Especially if you get like asked the right questions. Like for instance, if there are like array questions, then you should be perfectly fine, especially for like runtime. But then the on-site it gets much harder. So I think based on what you told me, without really knowing any of the results, your problem will probably be in fundamentally understanding these data structures and algorithms and when to use them and why, and just the basic runtimes of them, more so than trying to solve these problems. Have you done any leak coding?
Leetcode.
Yeah, leak code. Have you used leak code to practice?
Yeah, I've been using Leetcode to practice. So I'm just kind of going through them.
How many leak code problems have you done?
Um, so I've been mostly using Leetcode, but I've also been using like the educatives, grokking the coding interview.
Mm-hmm.
So most of my practice was with that. I did cracking the coding interview for like a little bit, but because I'm writing in Python and they're using Java, I kind of stopped doing that. And for Leetcode, hasn't been too many problems on Leetcode. Um, but there is like a lot of overlap between Leetcode and grokking the coding interview.
Mm-hmm. So how many leak code problems would you say you've done?
including like grokking the coding interview overlaps.
Yeah, sure.
I don't know, maybe like 50-ish,
Mm.
which is like a little bit on the low side, like 50 to 100. It's hard to like give a clear estimate. I know that yeah, I'd say like 50 to 100, like somewhere around there. I know that for the company I interview with next week, I'm planning on doing like 50 of their Leetcodes. And that's like in addition to the things I've done before. So yeah, I'd say like somewhere around that as a ballpark.
Okay. Based on your profile and everything you've told me and my past experience with interviewing candidates, I would say you're pretty underprepared. But I will see what I can do about it. I can give you the mock interview, but I think, um, I don't know how much benefit you would get out of it, but I can still do it. So I think really your issue would actually be trying to uh, mechanically solve these problems and understand why these algorithms are the way they are and the runtime complexities. Do you find yourself struggling with that?
Not so much with runtime and algorithms,
Okay.
but I think that's sometimes more about like finding the pattern. Like if it's a pattern I'm familiar with, I can at least understand it at a high level. If it's something that I haven't done before, then that's where there's definitely like a gap in my knowledge.
Okay. Okay. So the mechanical skill is something that I can test on, but it's not something that I can necessarily how to say that I can necessarily help you with. I can tell you what to do, but at the end of the day, it's kind of like on you to actually practice it. But I think but what I'm going to do is based on what you just told me, I'm going to focus on a problem that is more conceptual rather than mechanical. So it's going to be more textbook style, if that makes sense.
Yeah, I think that kind of makes sense.
Okay, because I think that you'll get the most benefit out of doing that. So let me share with you the Google Doc. So let me know if you've seen this problem before.
Mm-hmm.
So, given a binary search tree, find the kth largest element in the given tree. For example, suppose that I gave you this binary search tree. The
Mm-hmm.
second largest element of this tree is 30. So, if I were to give you k equals to 2, then you should be able to return back to me 30.
Okay. What's the time limit for this question?
So don't worry about the time limit. I'm basically just gonna go by until I get a good sense of your um until I basically get a good sense of you. Does that make sense?
Yeah, that definitely makes sense. Okay. So because we have a binary search tree, I know that we can use a in order traversal to get like a sorted array, and then we could also like iterate through that sorted array, and then probably implement like a heap um, to keep track of the largest element. Um, yeah, I think that would be the approach, but I'm also trying to think of like how I could work within um, the tree's general structure without using extra um, base with like the array and the heap. So that would be more like a brute force solution that I'll keep in mind. But now I'm gonna just analyze the binary search tree itself and see how I'm gonna work within that data structure. Um, so I'm just gonna write out a like test case just to like kind of guide me through it. So like you said before, with the k largest element. Um, so if k is 2, then for the k largest element, that would be 30. And the way that I would get to 30 is first I would want to get to the largest element overall in the binary search tree. And I guess I'd kind of just want to go back, like up the nodes, um, go back like towards the root until I'd reach until I went back enough to reach the kth largest element. So in this case, it would be at the rightmost node, which is 34. I go back up one from 30, one back up from 34, and I reach 30. So, 34 is like the first largest, 30 is the second. But I also want to test this with something else just to see if that algorithm would work out. So if it's something like 25 is the root, and then the subtrees would be, let's say 20 here. And over here it'd be like 30. And then oops. And then the subtree for 20 would be like, I don't know, like 14. And here it could be 24, since we still want it to be less than the root. So I know that if I am searching for the kth largest element, so let's say generally, like in this case, I'm just focused on like second largest element, and then I could slowly, instead of hard coding it, it could just be like through an iterative approach or recursive approach. But essentially, that means that I would want to focus on the rightmost side. And in that case, I actually want to revise the reasoning that I used before when I said that I want to use a heap, because I think that approach would work, but because it is very space intensive, and with this binary search tree, this already kind of organizes the nodes in a certain order, so I don't think that would really be necessary. So what I could start doing is starting out at the rightmost node, and then after I start out at the rightmost node, kind of just backtracking up and counting how many times I'm backtracking up until I reach K. So working with like a very basic example, if I have like 25, and over here I have 20, and over here I have 27. If I wanted to find the third largest element, then I'd go from the rightmost node, I'd go up, and if I'd go up to the root, that would be the second largest. And then afterwards, because there is no longer a way to like ascend, recurse upwards from the 25 at that point, I'd want to go to the leftmost node, the left subtree, to reach the element. So essentially, the direction would be from the right to the root, and then to the left, because that's just the in order traversal.
Just to correct you just a little bit, in order traversal would be LVR, but I understand what you're trying to say here. But that's just a technical term. It doesn't matter. It's just
okay.
Yeah.
Sorry.
Don't worry about it.
Okay, yeah, but essentially that would be, well, not in order, but it would be just like any traverse. Like this would be like the general order of the traversal in order to, so it wouldn't be the in order traversal. It would be kind of reversed in order, since we are looking from the largest to the smallest. So kind of like how a heap would work. So I'm just going to pseudocode out how I'd want the recursion to work for this, and then I'll start typing out the code. So if Um, is there any information given about the constructor for the root or the tree?
So just assume that you'll be given the node of the root, which in the example I gave you would be 27, and that
Mm-hmm.
you're given also k, the integer, the kth largest element.
Okay. So that would be like cake. It would just be like the root and k. And for k, I would know the node, so that would mean that I would know the value, and I'd also have access to the left and right
Well,
subtrees.
k is an integer, just to be clear, and
Oh,
root is
sorry, no, I meant for the root, I'd be given the value for like the node's value, like
yeah,
20, 25,
yeah. You can
etc.
think of it as a standard binary tree node class definition.
Okay, okay, that's great. I'll just make like a note of that. Um, Node, so I'll have the root value as well as the root left and the root right. Um, so I know that the class constructor is like a little off, but this is just like the general thing just for me to like remember what's contained in the class.
Mhm.
But going back to how I go about recursing through the tree, um, so I'd want to go through right to root to left. And as I'm doing that, so I'd want to check to see um, if the right subtree is null, or if any tree is, check if like the root is null, and if it's null, then return null. I have also another question about the inputs given. So when I'm given k, would k be within the range of the length of the binary tree?
What do you mean?
So sorry, I don't think I used the right terminology, but if I have, let's say, 5 nodes, k would not surpass 5.
You could assume k is any value. Your code should be able to handle that.
So if even if I have 5 nodes, k could be like 10.
Yeah, let's see. What do you think would be an appropriate return value for that in that situation?
I think that returning null would be okay, just because there isn't any 10th value, or just returning the smallest value in that case. Um,
I think null.
yeah, I think the
I think null would be would be a
standard.
acceptable value. I think it's acceptable.
Okay.
It's just really the point of that was really just to see you justify what and why. I mean, I would have accepted also throwing an exception as well.
Mm-hmm.
Yeah.
Okay, that sounds great. Yeah, so I check to see if the root is null, and in that case, I just return null. Or if there is no value that can be found for the kth largest element. Then after doing that, I'd want to have like a recursive call. Let me just put this on. Right. Then after that, I want to have like a recursive call for right subtree. And for that, I want to go to the rightmost node. So after going to back to like this example, after going back to the rightmost node, I'd want to work within that. So I'd be recursing from there on out.
Okay.
So I go to the rightmost node, and then afterwards, when I go to like its subtree, I see that's null, then returns back to there. And then after that, I want to go to its root. So for the root, So after I recurse to the leaf node and I start recursing upwards, I want to see if I want to keep like a counter basically of how many nodes I've seen from the largest element. And essentially, or I could just keep the counter for k. I could just keep the counter for k, so I'm not like wasting any space with like an extra variable or anything like that. So as I'm recursing upwards, I want to decrement k as I reach a new node with the recursive, like as I return from recursive call. And if k equals 0, then that's like the k, then return that node. So let me just walk through what this example. So I also forgot to look at the left. So I'm looking at the right. I'm decrementing k. I'm also be recursing through the root and recursing for the left. So if there's no more right, I go back up and it slowly just, goes through the whole tree like that. So going back to like my very basic example over here, I go to the rightmost node, 27. 27 doesn't have like a leaf node, a leaf sub. 27 does not have a right subtree. So at that point, I stop recursing. I go back up to 25, which is the root. And then I check to see what value k is. And then I go to the left from the root, and it would just follow that direction. So let me just try it out how it would kind of go in this example too. So I have 34 over here. I'm at like the rightmost node. I go back up to 30, which is the root. There is no left. If there is no left, continue. So this is like not the example with k, but just to check to see if the recursion is working okay. 27 and so forth. So yeah, I think this is kind of a bare bones approach to this problem, and I'm going to begin coding it out.
Before you start coding, I think you have an issue with your design.
Oh. I'm also going to be using a helper function.
Why do you need a helper function?
I think a helper function would just be better so that it would also give me like the new k value as like I'm decrementing it. But I don't think I necessarily need one in this case. So I'm just going to review what I have so far. So far, my base case is that the root is null, and if the root is null, I'm returning null. And as I'm doing the recursive call for the right subtree, I also want to maintain the value of k. So as I'm doing the recursive call, as I'm going up, I think this is where I want to decrement k. And I want to see if k equals 0. And if k equals 0, this is where I want to return the root instead of returning it at the end, because once I'm finished with my recursive calls, then I'm going up to the base case. Then I'm checking to see if it fulfills any of the base cases.
I think there's a simpler fix that you can just do. This
Uh,
seems like it would complicate your design quite a bit.
oh,
There's
simpler
definitely something simpler that you could do.
involving K.
No, just basically the organization of your steps, really. That's really it.
Um, okay, a simpler way. So I'm gonna think about the foundational knowledge that I have on binary search trees. Um, so what I could do is, so right now I'm kind of leaning towards an in-order traversal just because that would provide.
How about this? Undo what
um,
you just did and try to run the example I gave you. And let's see where that goes.
so without K, if K
Yeah,
is
yeah,
over.
without that. And I want you to try and write out what the value in your call stack is going to be.
Okay, I'll just move that up here so I can see that.
Sure.
Okay, so I checked to see if the root is null. It's not null.
Okay.
And then I recurse through the right subtree.
Mm-hmm.
So at that point, I have 34. And at 34, my k is going to be equal to 1. And I'm going to look to see if it's equal to 0.
Mm-hmm.
And now I'm going to be going.
Wait. Which step are you on? So you got to 34, and
Yes.
you're by recursing to the right subtree, sure.
Yes.
But then where's this k minus one popping in?
Oh,
Is
so
it?
what I
Oh,
wanted
okay.
is that like each time I recurse through a tree and I'm beginning to return the recursive
Oh,
call.
it's after the recursive call.
Yeah, so
I
after
see.
each recursive call, I decrement what k is.
Okay, I'll just move to a new line. Got it.
And then, so I'm like continuing to recurse upwards. I see 30. K is now equal to 0. And because k is equal to 0, um,
Slow down. Where is this recurse root coming in then?
um, so I wanted recurse root because like I said before, I wanted to go from like right to root to left. I wanted to also check to see if what the root was, but now that I think about it, it doesn't really make too much sense to recurse through the root because the function it already has the root in it. So I feel like that isn't really necessary, and it usually doesn't apply to like binary search tree traversals. So instead of doing like a recurse root, um, I could also just continue just recursing as is.
What do you mean recursing as is?
Um, like when I reach the root, I could check to see what k is at that value. If k has been 0, if k is 0, then I want to return the root. Otherwise, I don't.
So you're basically treating that as like one of your base cases or how you're handling things.
Yes,
Okay.
I am, but I think my concern about that is the fact that because right now the way that I've designed it, it decrements after each recursive call, like as I'm returning the nodes. By the time it's like 27, by the time I go to the root, I'm not quite sure if.
Well, you have this decrement k minus one up here, right?
Mm-hmm.
And then you have it k minus one down here as well.
Yes.
So you're recalling k minus one twice.
No, sorry. I meant for that to be one. Because when I was like doing the example, I realized it's better to just have the k minus one like along with the recursive call. Um, but I don't think that would apply anymore.
Okay.
But going back to recursing through the root, yeah, I don't think that would apply. I could just check to see if k is 0, and if k is 0, then return the root. So that could also be another base case. If k is 0, return the root, and that would be before before the recursive calls.
Okay.
Should I continue on with like the running the test case?
Well, then what is this recurse root? Because the way I'm seeing it is that you, like, let's say you're at node 30, you
Uh-huh.
recurse and call the right subtree, and
Yes.
then you get to 34, right? And then 34 has null, null, and so you are going to recurse. There's no right subtree, okay, returns, and then you recurse root again. So then you call
Oh,
34 again, and then
oh,
you
sorry.
yeah, so you end up with a stack overflow because you're gonna keep going root going in 34 over and over and over again.
Oh, okay. Sorry. I forgot to explain this better, but when the first time you said to reconsider recursing the root, I added this line in instead. So in that case, this wouldn't apply anymore. Because of case or I just like return the root.
Okay.
So in that case, I wouldn't also need this here just because, um, just like review like the general structure of my program. So essentially, the base cases are if k is 0, return the root, and if the root is null, then just return null. And I would recurse through the right subtree, and I'd recurse through the left subtree. And as I'm recursing through it, I decrement k for each recursive call.
Okay, let's walk through the example. So let's say you go all the way down to 34, right?
Yes.
You have decremented k, so then you visit the right subtree, which is null, so you return null. And then you do k minus 1 there, and then you recurse to the left subtree of 34, which is null, and then you go back,
Mm-hmm.
and then you go back up the call stack to 30, and then you do k minus 1 again. And then you go to the left subtree, which is null,
Mm-hmm.
and then you go back. So now you're at k negative 1.
Oh,
Does that make sense?
yes, that does make sense. Because I'm decrementing k at each recursive call when I only want to decrement k if it's not null. So if the root left is a null, then I want to decrement k. If the root right is a null, then I want to decrement k. So instead of doing the recursive call for the right subtree and then decrementing k along with that, I think it would be better um, if when the root left is not null, then I'd want to decrement k at that. Oh, sorry. If the right is not null, then I want to decrement k because at that point I actually have a value in there. So in that case, I wouldn't want to decrement k like in the recursive calls.
Okay.
And I think the same thing goes for as I recurse through the left. If the root left not null, that's when I'd want to decrement k.
Okay.
Okay, so I'll walk through this example and kind of see how that would work out.
Mm-hmm.
So I check to see if the root is null. It's not null. A is not 0. And then I recurse through the right subtree. I reach the rightmost node. I reach 34.
Mm-hmm.
And then, so the root right is no, I don't do anything. And then I go over here, and at here is where I want to decrement k. And I recurse the left. Left is also no, I don't do anything in that case either. And then I go back up to 30. So at 34, k would have been decremented. So that means pretty much that, like, for each root that is not null, that's where I'd want to decrement k.
Aren't you already doing that? You're decrementing k here, right?
Mm-hmm.
So are you decrementing k again?
You mean for the left and right subtrees?
Yeah, because it looked like you were about to do that again. So I don't really know what you're trying to do.
Mm. Actually, I do want to revise this. I think that instead of, because after walking through that example, I think that the major problem I am having is with decrementing k, and I think that I want to decrement k if the root is not null, because as I walk through the example, I realize that if I'm looking through this example here where I have 34 and I have my leaf node on both subtrees, because right subtree is null, don't decrement k, I go to the root, and at the root that isn't null, that's when I want to decrement k. I go to the leaf node left subtree, also null, don't do anything there. And then the recursive call continues upwards. So instead of decrementing k at those instances, because the recursive call for each of the subtrees is already returning up to the base case, once I've maxed out the path in that direction, instead of repeatedly just doing that, I think it might make more sense if just to decrement it when the root is not null, because all the nodes will have been roots at some point. So I'll walk through this example. Okay, so check to see if the root is null. It's not null. A is not 0. Then I'm going all the way to the recursive call over here. I will also have to change the order for this later on. But
I'm
this,
going to say right now you're at 30 minutes, and I don't, based on what I've seen, I don't think you're going to get to the right answer until about 45 minutes.
okay.
And I already understand what your problem is actually. If you
Mm-hmm.
want to keep biting at the apple, that's fine, but I don't think there's anything more I need to see.
Okay.
Right. So I'll stop the time. So what do you think? Do you want to keep trying, or do you want to stop?
I think I want to stop. I think it would be great to just hear some feedback.
Sure. So I'm very curious to see what you're thinking right now. Do you think the
Mm-hmm.
interview is going like well, is not well? What do you think?
I don't think it's going too well. I was planning on reviewing trees again, so I am a little bit shaky on trees. I think that um, when I had the brute force solution with the in order traversal, putting them into array in a heap, I think that brute force would have been okay, but I don't think that in like an actual interview that would not have been an optimal solution. Um, so I think they would have expected something with a tree traversal, but I think that with the tree traversal, I was getting very caught up on knowing when exactly to decrement K, and I kept on going wishy-washy back and forth on doing it for the recursive calls and everything. So I think that understanding the general fundamentals of tree traversals is something that I definitely need to go over.
From my perspective, your first 15 minutes were actually quite phenomenal. And then the moment you had to debug your own recursion, never mind the code, you ended up tripping up quite a bit. So
Uh,
everything here tells me it's nothing to do with trees. It's your ability to understand recursion that was the issue.
okay.
So let me share with. Let's go over the replay, and I will tell you, and I'll go over it. So right now, so I have a little timer at the bottom, and I think the way you break down the problem is actually quite good. Um,
Okay.
I like how you basically tried to come up with your own example, try to understand it, and you caught on to, oh, what is the error case, what should happen here. I think that was very good.
Mm-hmm.
I definitely would have liked to see you display all your options, talk a little bit about them more, like for instance throwing an exception,
Mm,
being able to show that you understand all your options and then choosing one option and justifying it would have gone very, very well. I think that is something, but that's small compared to everything else that we're going to talk about here. So
okay.
I like this very simple example. You did identify that it's a reverse in order traversal where you do RVL, but
Mm-hmm.
I think there's a disconnect between your conceptual understanding and your ability to execute. And this is what I
Uh,
talk about. And so what I'm talking about here is when you get to design step. So this is fine. This is all reasonable here. You
okay.
decrement 0, left, right. And really, when I saw this recurse root, I already knew that you did not have an understanding of recursion.
Mm-hmm.
And then you ended up spending the rest of the time just trying to go through the example and then patch your design, go through the example, patch your design. So if I had to guess, when you practice your leak coding, are you the kind of person who just throws random code at the compiler and hope that the compiler accepts your solution?
Um, well, because I haven't done too much lead coding, like I said before, I was using mostly the patterns. I kind of just look at enough patterns until I kind of have a general structure.
Mm-hmm.
And then I'll look at the solution and I'll kind of think through it and then write my own notes on it and then like use that.
Okay, but like let's say you get a wrong answer on leak code. Do you actually go in depth in your design and try to bulletproof it, or do you just make one change to your design and then throw a new submission at Leetcode and hope that it works?
The latter,
Yeah,
unfortunately.
yeah, that's basically what I picked up here when you kept trying to
Mm-hmm.
patch your code and like, oh, this, and then I said, well, let's run through your example again. And so what I really wanted to see was for you to really, essentially, the right answer is replace this recurse root with the last two lines over here. That would have been the that would have probably gotten you the right answer.
Oh, that's
Um,
very close.
it was pretty close. Or at least after you visit the right subtree, then then you will evaluate it. Or left subtree, um, that will get you to the root, and then inside that, that's your visit. So again, that's your disconnect between the RVL,
Uh,
and I'll show you in the Google Doc what I mean. But essentially, that probably would have gotten you the right answer, at least based on my understanding of
mm-hmm.
what you're trying to do here. But overall, you have this thrashing problem when it comes to patching your code. So let me show you how I would have done the problem, and maybe they'll make a little bit more sense. So
Okay, that sounds great.
so yeah, I think I would have done exactly the first 15 minutes. I don't think I could have done it any faster. I think
Mm-hmm.
you had pretty good optimal time on that. So if we're going with the RVL traversal, then
Mm-hmm.
yes, your first base case is check null. If null, return null. Um, and then after that would be to check our right hand side. And then this is where your visit comes in because you're visiting the right hand side. And so if k equals 0, then return because this is our visit case. Visit case, and this is our right hand side case. Visit case, and then return this. Return current. Let's say return node, and then the left hand side case, um, check left hand side, and then if k minus minus. Now, why does this work? Because the traversal case just determines what node you are visiting,
Mm-hmm.
and then the visit case is when you do the actual evaluation. And so let's take this example for instance. I'm going to copy it down here. So let's say I do k equals to 1, right?
Yeah.
Just for argument's sake. K equals to 1. Then I expect my answer to be 34. So then my call stack would be I'm starting at 27. I'm going to check right hand side, which will get me to 30. So side 30, right hand side, get me to the right side, and then 34, right? And then I'm at right hand side, and then go to right hand side, and then I'm looking at null. Null case is going to return null. Cool. And then I can do k equals dec, and then k minus minus. So then I assume I will make k a class variable. So if I'm going to do this, so then k is going to equal to 0 now. And then if I'm in my k equals 0 case, then I return no. So great, I'm going to return 34, which is exactly what I expected. But then the right hand case means that, oh, well, now that I'm back at 30, check the right hand case and return if right hand case is not null. And then I mirror that over to the left hand side. That case is not equal to null. So that basically is what I'm doing here. So, but let's take it up a notch. Let's say I have k equals to 2. My answer would expect to be 30, right? So then going to the recursion example, 34 decremented k equals to. So now I'm at 34, right hand side, left hand side, pop back out. Now I'm at 30 with k equals to 1, right? So then now let's call it. Now we're at the visit case. Visit case k will equal to 0, and then do the evaluation. Great, I just returned 30. So that's what I expect. So far, doesn't make sense.
Yes, I think that does make sense. Like you're recursing all the way to the right subtree. No, you have leaf. You have leaf nodes. Then you start visiting the root. Yeah, I think that makes sense. I think then in that case, the general structure is instead of doing something like recurse root, what I think would have been better would be just to do root evaluations. So like at that root, like what would I want to do? And that would be in between the recursion, like when I did the right root left. So because the root was in the middle, that's when I'd want to do the evaluation as opposed to recursion, which doesn't really make sense in that case.
Yeah, a better way that I've had students understand recursion is that for the recursive step, just think of a function foo, which basically does exactly what your recursion does, except you need to define inputs and outputs. So, what does this mean? This means that for your recursion function, you expect to pass in, for the sake of simplicity, k into k, and you also want to pass in node root, right? So then for foo, which is some arbitrary function, let's just say that it takes in int k, node root, and returns root as what returns a node. And so what do these represent? So k represents our counter, root represents our current node we are looking at, and the return value is the matching node to k. So then think of foo as this magic function that does all this. So what does it look like in code? Well then, and you would call foo here. Foo. Call foo. So then in terms of code, this would look like something like, I'll just copy this here. So then here would just be if, so node right hand side. So if root equals to null, return null. And so here, our node right hand side will equal to foo k.root. So which means that we'll assume that k k this a class variable just for now, just to simplify
Okay.
things. And so we'll assume that after I call foo, that k decrements by the amount of nodes in the right hand side. So in our case, if we go back up to 30, then once I call foo on 30 on the right hand side, then I expect k to decrement by 1, right?
Yes.
If I call it at 27, I call on the right hand side, then I expect k to decrement by 2.
Yes.
So let's assume that for our case of argument. And so based on our definition, that will return null if we can't find it, if k doesn't satisfy our condition. So then if right hand side does not equal to null, return right hand side. Otherwise, when we enter here, we know that right hand side is null. We haven't found what we are looking for. So then that leaves, well, since I'm ordering RVL, then maybe the current route that I'm on could be what I'm looking for, right?
Yes.
What if route is what I'm looking for? Okay, so then our condition, we'll just do k minus minus, because I need a decrement. Because if, let's say, in a magic world, we only look at 27, right? And 27 had no left tree or right tree, and we looked at k equals 1. Well, then we would expect 27 to be the answer. And our condition is like k equals 0. So then I go to 27 with k minus minus, which means k equals 0. So then if k equals 0, return root, because hey, we found it, right?
Yeah, makes sense.
And so we decrement k every single time we look at a node, right? So then if that's not the case, then we will recurse back. So then just do the same to left-hand side that we did to right-hand side here. I'll just do it shorthand. And then at that point, we'll have that null check for the left-hand side. But let's say, in the case that left-hand side didn't find it, well, it's neither in my right-hand child, it's neither in my right subtree, it's not in my left subtree, and it's not the current node we're looking for. So by process of elimination, we've eliminated every single possible node that are ourselves and our descendants. So it must be a value somewhere else. So that's why here our default value will be returned null. And that's how I would assemble the code if I'm looking at this. Does that make sense?
Yes, it does make sense, because going back to like the very basic example I was working with, where you just have like the root and the two subtrees, you would have to look at each of the subtrees and the root, because those are the only cases you have. The evaluate in each case was feasible.
Yeah, more or less. And the beauty of doing it like foo is that you don't have to think of it as a recursion. So now you can just do this. Boom. Magic.
So for that, it was just changing it to like whatever the recursion is. Okay, that makes sense.
Yeah, so two functions are equivalent is if for every single input we get the exact same output. And by our definition up here, we basically define that. The only difference is that it's just stylistic to help us really look at these functions without, some people have this trouble of, I called the recursion, let me jump into the recursion. But the fact is that recursion is just a function that calls itself. So that's why we use foo, to basically just not get ourselves caught up in the recursion, which I think is probably what happened to you.
Okay, so instead of having all the recursive steps like within the main function, maybe using like a helper function that I'm assuming is like, doing whatever, would be better, just so.
Yeah, I mean, like as a crutch to help you learn recursion. Of course, at the last step, just eliminate foo and replace it back with recursion, because by our definition, we are assuming that, recursion and foo are equivalent. It's just like, the difference between iterating over a structure versus recursing over a structure. Both of those are equivalent. So you can think of these functions as interchangeable in that regard. And it's just really a crutch. Eventually you'll get to a point where you don't necessarily have to do this.
I think that makes sense. Just understanding how the function is going from like one thing to another, like within itself.
Hmm. Yeah, and so the key to this is the you said RVL, right? So you at each um each evaluation, you need to understand what you expect going into the function, what you expect coming out of the function, and any class variables that might be modified and what the modifications mean.
Mm-hmm.
So in this particular case, instead of passing in k, which we could do, and in that case we could just return back a. If we wanted to not have a class variable, we could just return back a pair of node and k. You know, um, in order to maintain our copy of k, if we didn't want to mess around with class variables. But I kind of just did this just for the sake of ease. Regardless, the key is this evaluation here is that at every single node that we look at,
Uh-huh.
we decrement k.
Yes, I think that was the main part where I was just having trouble on where to place that.
Mm-hmm.
I think I fundamentally understood that that operation would happen, but I just wasn't sure how it would fit into the traversal that I was thinking of.
Mm-hmm. And so, what I want to see, I think, what would help you
Uh-huh.
is if you blocked out like recursion like this and just made it foo, and you only focused on one node. That way, if I gave you something like a tree, like let's say a, what's it called, B and C, you don't care what the value of of B and C are. They can be leaves, they can be null, they can be whatever. They can have a subtree, they can be whatever that you want it to be. But the point is to block this off so that way you don't actually care. You don't go deeper into the recursion. You only care about what you put in and what
Mhm.
you get out when you call the function on them. So I'll put that. Only care about input and output to foo B and foo C. So if by our definition for foo, then and we pass in B, then
Mhm.
I'm going to pass in my node, and I'm going to assume that it's going to give me back null if it can find our target node in B or B subtree. I don't care if it's B itself or a descendant of B, and same thing for C. And we also assume that as we go along, that we decrement K every single time we visit a node. Now, that means that, let's say A could be my candidate.
Yes.
That means that I need to decrement K in order to keep in line with this definition. Every single time I look at a node, I
Mm.
want to decrement K. And so the last thing is, what is our condition for returning a non-null value if K equals 0 at the node I'm looking at? Does that make sense?
We also want to make sure that it's not null.
Yeah, it's because by our definition, what we expected for the return value is that it will return not null for the target node that we want, and will return null if we haven't found it.
Sorry, I was just like typing that out.
That's fine.
Um, yeah, that makes sense because going back to like the basic example, I'm looking at the right, like with just the root and the two subtrees. I look at the right if it's in the right. Return the right if that's not null. Look at the root.
Mm-hmm.
Do the root evaluation. Look at the left, and after all that is done, return null if nothing's been returned yet.
Mm-hmm. Yeah, that's pretty much it. And so that's all I got for you. I think basically comes down to a fundamental misunderstanding of recursion, getting kind of lost in this. That's really it. But I'd like your approach actually. I think it's a lot cleaner than what I've seen a lot of people do, at least for the beginning parts. And again, and this was just a conceptual misunderstanding, which I think it's very easy to get over. I think when I coach people, what usually happens is that they actually struggle with what you seem to make really easy, which is the ability to break down the problem and understand it. So that kudos to you. That was really good.
Oh, thank you. But yeah, in that case, I definitely will review recursion more just so that, when I'm doing like street traversals or anything really, I'm just able to understand more about
Mm-hmm.
how the recursive call is like trickling down and then coming back up again.
Mm-hmm. Yep. Just think of it like a black box. I don't care how it's done. All I care about is like I'm going to throw it in, and I'm going to get
Uh-huh.
something out. But whatever I've defined that black box to do, I need to make sure my current function will do it on an individual level.
Um, I think that's the part of where I'm getting like a little tripped up about
Mm-hmm.
because you throw something in, usually you make like some sort of modification when you're recursing through it.
Mm-hmm.
And then in this case, it would be like calling the subtrees. Then when you're looking at to see how it's like an individual component in the program, I think that's where I'm getting a little tripped up about. But I think if I do enough Leetcode practicing, um, it'll just slowly I'll just become more familiar with that.
Okay, I'll just quickly go over this again. Hopefully, maybe I didn't explain that well. So let's say k represents our counter. Every single time we will decrement k. We will decrement k every time we visit a node, right?
Yes.
And if the current node we are looking at is the one we want, then we return it. Right?
Yes.
So, what is this condition here? How do we know that this is the one we want? How do we know if this is the one we want?
K would equal to 0.
Mm-hmm. So we can decrement k every single time we visit a node. Well, it turns out when we're in the middle of our function right here, we're gonna visit that node. So hey, let's decrement it. So, like in order to adhere to this contract that we want, because every single time we visit a node, we want to decrement k, and then we do this evaluation here. So you can see like how if we set up the policy, we just need the code to reflect that policy. Is that a little bit easier to digest?
Yeah, I think so.
Okay.
Okay, I think that it is. I think I'll probably sit with it a little bit longer, but I think it does start to like make sense on like where to place it now.
Mm-hmm. Yeah, just don't always assume that the base case is the very first thing that you need to handle. Because I noticed that you had this
Yeah.
issue of like tagging it at the very top. Well, maybe not. Again, because you did an RVL traversal or LVR traversal. It doesn't matter. Well, one of the base cases is null for sure, and then you could just eject from there. But then, if there might be another base case, but you don't evaluate necessarily right off the bat, you might evaluate it later.
Yeah, like when we're returning, no, because we haven't like found it yet.
Mm-hmm. Yeah, but that's everything I got for you.
Okay, that sounds really great. I know you also said that you would also test my mechanical skills. So I was wondering if you had any feedback on that. I know that I didn't actually get to code it or anything.
I think your mechanical skills looked pretty good, actually. Your ability to dissect the problem and understand what you wanted to do was actually quite nice. And definitely, I think if you, how do I describe this? I don't think you need too much on the mechanical front, actually.
Uh-huh.
I would definitely say maybe check your ability to come up with examples and test. Because from what I saw, when you came up with your examples, it seemed like you were kind of doing them almost like, I would say, incomplete. Because you came up with like just a 3-node structure, but with like one root node and then with 2 children, and that's it. You didn't really consider them in a general sense, but that of course that's kind of hard to do until you really understand recursion, traversal, and what your code is really meant to do. Um, so it's kind of a catch-22. It's like you don't really get to that point until you understand the recursion, but then you need to understand recursion to get to that point too.
Be able to do that.
Yeah, it's like, being able to group every single test case, every single possible value into a generalized
Mhm.
formula. Like what I did here, when I said ABC, doing it like this. Well, I don't care if A, B, C, I don't care if B or C are null. So they could be both null, one could be null, neither could be null. It doesn't matter. And then you might also have a case where you care about the ancestor, like Q. Well, you might pass in Q as into your evaluation function as well. Well, then now you have to have all these possible combinations of q may equal to null or not null, and then a and then b does not equal to null or not null, and then c equal to null or not null. So there's 8 possible combinations as you can have. But, so in some cases, left child and right child could be treated the same, so maybe not. You can combine B and C into exactly into the same, so then you might only have to deal with 4 possible combinations. And so it kind of gets a little bit murky, and I can't really tell you how to do that exactly. It's like you kind of get a sense of what matters and what doesn't. That's the best way I'll describe it. Don't worry about it too much. Eventually, when you get good at testing your code, then it will come naturally.
Okay, yeah, I think that makes sense. Like some things definitely do come like with intuition after time. But thank you so much for the detailed feedback. I know that in the beginning you said you had some worries about me being underprepared. I was wondering like what your thoughts on that are.
I think your problem solving ability is actually quite nice. I think what I would do if I were you, I would spend less time on the patterns, more time studying on the raw conceptual ideas, like go through a textbook and a little bit more detail, because we didn't even get to runtime. So I think more of the theoretical would be very good for you. Just brush up on that, and then try to apply those concepts before you even hit the patterns. Because from my point of view, patterns are only useful to help you get faster at things. But if you don't have the raw understanding to begin with, then it's almost worthless, because you won't understand, wait, why is this pattern applicable? How does this pattern actually work in these situations?
Yeah, that makes sense. Yeah, because I do understand like the general tree traversal structure, but because I don't have a good conceptual understanding of recursion, I can't really utilize that to the fullest.
Right. It's like you'll know what it is, but you won't be able to apply it. And as you saw here, you were kind of thrashing about with debugging your recursion because you didn't understand recursion.
Yeah.
So, and a lot of DFS and traversals are built on top of that. So it kind of messes you up.
Yeah, that makes sense. Thank you so much for the detailed feedback. I really appreciate it.
Yeah, for sure. Just out of curiosity, do you watch my YouTube channel or did you read my guide?
I read your guide.
Ah, that's why. Yeah.
Oh, why?
Yeah, the reason why is because your approach seemed to be quite in line with what I would have done and what I wrote in the guide. So I was wondering if you took cue from that or you mostly just read it for resource recommendations.
Yeah, I did like read through it and I also like really enjoyed it. It was like super informative, and it was also super honest too.
Mm-hmm.
Um,
Yeah. All right. Do you have any other questions?
no, I don't have any other questions.
All right, for sure. Then I guess we'll stop here. I'll share with you this recording once I get done uploading it.
Yeah, great. Thank you.
All right. Thank you. Take care.